Inside silicon, the technology behind everything.
In the world of high-stakes chip design, one tiny mistake doesn't just cause a minor bug. It can completely wipe out a billion-dollar program. Today, we're going to explore how the most complex machines humanity has ever built can be brought to their knees by a single, invisible error. Let's get right into it. It always starts with something that seems like nothing at all. A single connection, a via, that's off by just a couple of nanometers. What's the big deal, right? Or hey, maybe a spacing rule gets missed. One wire is placed just a little too close to its neighbor. Seems trivial. And the result of that trivial little mistake? Complete and utter catastrophe. An entire chip program, years of work, billions of dollars, just gone. How is that even possible? Well, that's exactly what we're here to break down. Okay, so to really understand the risk here, you first have to appreciate the insane scale we're working at. We are operating in a world that is almost impossibly small and unbelievably complex. So first thing, stop thinking of a chip as just a simple circuit. A modern AI chip is more like a sprawling, hyper-dense city with tens of billions of components all packed into a space smaller than your fingernail. When you're working at that microscopic scale, there is simply no such thing as a small mistake. This incredible density leads to a really brutal, fundamental truth about hardware, something that every single software developer should probably have tattooed on their brain. In the software world, hey, no big deal, right? You find a bug, you push an update, you send out a patch. Easy. But with silicon, once that chip is manufactured, that's it. It's frozen. Every single transistor, every wire is locked in place. You cannot patch physics. The errors are permanent. And as we shrink down to these advanced nodes, we're talking 7, 5, even 3 nanometers, our margin for error just completely vanishes. Think of it like you're walking a tightrope. On one side is heat, on the other is electrical interference. The transistors are so close that electrons literally leak between them. Wires create crosstalk. Managing the heat becomes a primary design challenge. At this level, it is way less about pure creativity and all about managing physical risk.
You know, when a chip fails, most people imagine a logic bug, some flaw in its digital brain. But the reality? It's far more subtle. The most catastrophic, program-ending failures are physical. They are the silent killers lurking in the very fabric of the chip itself. Let's meet our first silent killer, electromigration. I want you to imagine a river that's flowing so incredibly fast that it starts to physically erode its own banks. That is exactly what's happening here. The flow of electrons is so intense that it literally rips apart the tiny metal wires that connect everything.
And here's what makes this so absolutely terrifying. A chip with an electromigration flaw, it will pass every single test in the factory. It works perfectly at first. But months down the line, out in the real world, sitting in a customer's server rack, it fails. It's a ticking time bomb that you baked directly into the silicon. Okay, our second silent killer is IR drop. The easiest way to think about this is like water pressure. If you've got a huge network of pipes, the pressure is always going to be lower at the faucets that are farthest from the pump, right? Well, in a chip, the power grid is that network of pipes, and IR drop is when the voltage, the electrical pressure, sags in certain areas. So why is this a massive problem for AI chips specifically? Because they have thousands of little processing units that all demand power at the exact same instant. This creates an enormous, sudden spike in current demand. And if even one part of that power grid is too thin or too weak, the voltage collapses and you get these random, completely untraceable failures. And as we push to more and more advanced nodes, the consequences of these physical errors just get exponentially larger. We're not just talking technical problems anymore. Just look at that number, $300 million. That's the potential price tag just to fix one of these mistakes and create a new set of masks to manufacture the chip again. That's for a single respit.
But honestly, the financial cost is only where the pain starts. A failed chip means you miss your market window. It means your biggest customers, the hyperscalers, they go straight to your competitor. Your entire product roadmap gets thrown into chaos, and your company's hard-won reputation for reliability, it's shattered.
So, given these absolutely insane stakes, how do professional teams actually build chips that work? Well, the answer isn't about being cleverer than everyone else. It's about being more disciplined. Success here isn't about some single silver bullet. It's a rigorous, methodical process. The top teams use multi-stage verification to check every last detail. They have entire teams dedicated to signing off on power and thermal integrity. They build in conservative margins, giving themselves room for physics to be messy and unpredictable. And maybe, most importantly, they obsessively study every past failure to make sure it can never, ever happen again.
This quote really gets to the heart of the professional mindset. For any of you studying to get into this field, this right here is the key takeaway. Great chips are not about being aggressive. They are about being carefully constrained. It's not about chasing flashy performance at any cost. It's about delivering absolute, unquestionable reliability. That's what separates a student project from production silicon.
So after all this, what's the single most important lesson from our deep dive into the hidden world of chip design?
It's this. The deadliest mistakes are the ones you can't see. They're the subtle, almost invisible flaws in the physical foundation that only reveal themselves after the damage is already done and millions of units are already out in the world. And this leaves us with the critical question for the entire future of technology. We are constantly demanding more innovation, more performance, more efficiency. But this whole future is being built on a foundation of unforgiving physical laws. So the real challenge for the next generation of engineers, maybe for you, is how do we balance that relentless ambition with the profound discipline that physics demands?
Inside silicon, the technology behind everything.